around early 1600s. So just like if you go on to eBay or Etsy or anything, you type in astrolabe and you see all the things, what you'll see mostly are these really elaborate, pretty devices that are solid. They've got all this stuff on them. Whereas a mariner's astrolabe, which are much more rare, really just do degrees, and that's it. Okay, and in fact, they're not solid. You know, they've got gaps for quadrants so the wind can blow through them, so when you're holding the astrolabe, the wind doesn't mess you up. It's bad enough the ship's rolling around. But the wind does it too, that's a problem. Well, this device actually does all kinds of things other than measure the altitude of the sun. It'll tell you the time, it'll tell you certain planets when they're rising or falling, it'll tell you certain things about the stars, all to a certain amount of accuracy, but only if you're at latitude 51.5 degrees north. Right? If it's some other latitude, you're just flat out of luck for all those other things. So really, the only thing it does really well is, in fact, it doesn't even do that really well, but it for its day it was fine.
It was a Swede, maybe?
Yeah, it will tell you the altitude of the sun, right? And so this one, they really don't want you to look at the sun because this is a really tiny little pinhole. So the deal on this is what we're going to do to keep the normal thing, it takes forever. I'm going to have one person who's not seen one of these before demonstrate it, okay, and then which I'm not doing a very good job at it. Anyway, demonstrate it, and then just sort of we'll pass it around over there. So the idea is this little guy has a tiny pinhole, and this little guy just has a cross on it. And the idea is you project that little spot to the sun. Oh, I don't know. Maybe I can't do it. I don't know.
Put the shadow here.
Yeah.
Then
What?
you can see
Line up the shadow.
Oh, okay. That's gonna help. Like I have not used this all that much, to tell you the truth. So
What is this called?
this is called Gunther's Quadrant.
Okay, thanks.
So what I'm trying to do is I'm trying to get the little. I almost saw it. Hang on. There we go. Is anybody seeing
There
this
it
little
is.
dot right here?
Yes.
Okay.
Oh,
Yeah. Okay. There's the little dot. It's right on the cross now. It waits for the little plumb bob to stop bobbing around. I just messed it up again. So hang
I think
on.
they should make the target bigger so it helps you kind of line it up.
The bigger it is, the easier it is. Yeah. That is true. The bigger it is.
there, with the less accuracy.
there's something way over
There we go.
Yeah.
There we go. There's right there. And now stopping it there.
Yes.
And it's down at about 11 degrees or so. So I'm going to have somebody who's not used one of these before, which was just me a minute ago. I've used it a couple of times. Go ahead and try it again. Do I have a volunteer to want to demonstrate it? Okay. There
That'd
you
be
go.
really easy to accurately line up in 6-foot seas, wouldn't it?
Yeah, it would be. You've been out even on the California on a nice day. That would be a tough order, wouldn't it?
What did you say, 52 degrees north?
If you're at 51.5 degrees north, it
51.5.
will be able to do all those other nice things for you.
51.30.
Is that,
But if you're not,
that's
too
pretty,
bad.
that's pretty far north. Is that Greenwich?
No, I wasn't joking. It actually
joking?
has stamped on it 51.5 degrees
The,
north.
the English Channel is 51 something.
Yeah, so this is
I wonder
meant
if
for
that's
English.
Greenwich.
So Greenwich, it might be Greenwich. It could well be.
So this thing was hard enough. Try finding one that says 33 degrees north. You know? You're just not going to find that. There's two twilights every day. There's the sunrise twilight, and the sunset twilight. And so what comes first in the morning is civil twilight, and then, well, let me make sure that I don't get that wrong, okay? So what comes first in the morning is nautical, and then civil twilight. And then what in the evening for sunset, civil comes first and nautical. Just it helps me remember that people in civil service work shorter days than sailors do. Okay, so that helps out in my mind for that. So we went through the process with that, and we talked a little bit when we used the nocturnal and everything about how to find Polaris, right? And that is you find the Big Dipper. And the two outermost things of the bowl of the Big Dipper are called the pointers, and they point towards Polaris, the North Star. David.
Dr. Ashley, please use the microphone.
Oh, the microphone. Has anyone found the microphone? Because it was missing earlier today. Okay. Maybe some of you can move further forward, because I don't know. David, is there a microphone back there? Are there any on the podium? The plastic, well, there's this tub here, and they're not in that, so. But, yeah.
Put them inside. Not just like inside where I normally put them. That's good. We're good.
You found one.
Yep.
David, thank you. Is that better? Okay. All right, so back to Polaris or any other star. You need to be able to predict twilight, and then the other thing is find the star. Well, Polaris is pretty easy to find. You use the two pointers of the Big Dipper, the two pole, the edges of the two stars that define the outer edge of the Dipper, and they point towards the North Star. Now, for us, that's pretty close to being Polaris, but of course, it moves. The stars aren't fixed in space all the time. The Earth actually, its axis moves around in the celestial sphere on about a 26,000 year long cycle. So in the time of Homer, the North Star was actually Kochab, not Polaris. And it's been different stars at different times. And that's just this wobble on the Earth's axis that moves it. And that's why when you look at any of these stars, there are slight changes over time, but they don't move to the same degree that other things in the sky, like the sun and the planets and the moon, move. In addition to that wobble, which is called precession, there's other within it little bitty wobbles called nutation, caused by the fact that the moon is kind of jerking the Earth around a little bit, along with the sun, and it's doing these little oscillations, okay, as it moves around this wobble. So there's the combination of those two is what causes us to need to do that you don't have just a fixed number for every single star, that it does move around some, and why every daily page in the almanac gives you the GHA and the declination for a particular star. Question? Precession was the 26,000 year wobble, big, wide wobble. And nutation are the little oscillations. Nutation, little oscillations. The combined effect of those two things are why we have to go to the daily pages for the given star, okay? Why we need local hour angle and that sort of thing. So once you find Polaris and you're in the northern hemisphere, you can see it. Then the problem becomes, finding the other stars, to be able to shoot them. Now, one trick is if you know the sky and you can look up at the sky, you can then set your sextant to 0 degrees, 0 minutes, 0 seconds, aim it right at the star, see it, and instead of bringing the star down to the horizon, bring the horizon up to the star, okay, while constantly keeping your eye on that. Another trick is to increase the field of view by lowering the magnification. All right, so some of us, our sextants are 4 power, some of them are 7. Sometimes you can get just a tube that's a 0, and that gives you more of the sky to look at, which you can identify the star in and do that number. And it's helpful to be able to know the sky enough to find the stars. But of all the zillions and zillions of stars out there, there's only 57 of them really that the almanac or any of these other tables give you the solutions for. So that's all you really have to know, and almost no one knows all of them or uses all of them. Some of them are useful for the northern hemisphere, some for the southern hemisphere. As it turns out, though, that at twilight, if it's twilight, you really can't see every star, and most of the ones that you can see are the ones that are identified in the Nautical Almanac, okay? But that does pose another problem, and that is if you can't see the whole sky, and you're used to looking at the whole sky to find the particular stars and be able to name them, most of those other things that you might be used to using as sort of guideposts for you, those are gone, right? So it's just these stars. And that makes it a little bit of a problem. I should say it's less of a problem in the morning twilight, because you could be up when it is really dark, locate where all those stars are, and then as the sun starts getting closer to the horizon, all those other stars start fading out and you're left with the navigational ones, okay? It's a little bit tougher in the evening twilight because you're starting with, daylight with a clear sky. And the first things that appear are those stars you want to use. And by the time you see all those stars you're used to, now you can't see the horizon anymore. So a lot of people prefer to actually, if they're going to do star shots, do it in the morning and use that. Now there's various means of learning the sky. I passed around a handout to you last time, That's a pretty good map for the sky. It's produced by Celestere. There's other kinds of aids for doing that. I'm going to pass these around, so I kind of want them up. These are called planispheres. You can get them, in national parks, or you can get them, on Amazon and so forth. And they typically produce the night sky for the latitude near where you're at. So one of these is the night sky for latitude 30 to 40 degrees. I'm going to pass that around. The other is a planisphere. Let me get it out of its little container. And you can see that you've just, you adjust for the date. And this is latitude 30 degrees north. So they're really good guys, for really good aids for helping learn the sky. But it's got all the stars there. And so you can kind of learn where they are relative to each other. But for evening twilight, that makes it a little bit tough, What you really want is something that'll tell you, okay, what direction do I aim my sextant and what altitude do I set it at? Look in the direction of that altitude. Oh, there's that star, right? That's what you really need. There's some things that can help you with that, like some of us have programs on our phones. You just aim it and it'll tell you what star that is. Okay, but then you've got to translate that. So really the best device for finding that is something called the 2102D Starfinder. It was produced by the Hydrographic Office at one time, but not anymore, unfortunately. And I'm going to use this on Ladybug and not pass it around. But what the device consists of is a white circle, white disk, and one side has the northern hemisphere stars, and the other has the southern hemisphere stars. And then you see there's a whole bunch of clear disks that look like this, each for different latitudes, okay? And north and south, depending on what's. So and there's a little explanation how to make it work that comes with it, okay? Now, if you really want to get into it big time, there actually is a book that goes along with it called the Starfinder book, all right? And that'll, that goes into much more detail than the little explanation. But the truth is, it's really pretty simple. So, what I have done is I've taken the disk here for latitude 35 degrees north, close to us, and I have put the little hole in the middle of it on the little nub. And, okay, so, how do oh, there we go. Okay, that's showing what we have. And so as you rotate this around, okay, as you can see, all the stars on this disk, some of them are brought within the scale, or the grid here, okay? And what is that grid showing you? Well, first of all, this line here is LHA of Aries, just like we had to find for the North Star, LHA of Aries. So you find that and you work that out, and you put this little arrow on whatever the LHA of Aries is after you've predicted twilight. So you can already predict what stars you're going to look at. You know when twilight's going to happen, sometime during the middle of that. You calculate for LHA Aries, and then you set this up for that, and then it tells you the stars. Now let's say you want to use the North Star to get latitude and one of these other ones, right, to cross it with. Well, one of the other good ones is, Arcturus is one. If you look at that thing that I passed out to you, Arcturus is pretty easy to find because you've already found the North Star by looking at the pointers, okay, the two stars that define the Dipper. If you follow the Big Dipper around, the handle of the Dipper makes an arc, okay? Follow that arc around on the same kind of curve, and the first bright star you come to is Arcturus, okay? So that's an easy one. And the combination of Arcturus, if you can see it, which you can a lot, and Polaris will give you a position, actually, okay? So that's what we're going to work out now.
So wait, say it again?
The combination of taking two shots, one of Polaris, one of Arcturus, will give you a position. Each one gives you a line of position. And what you want to do is have them cross at a nice angle. Now, how do you know how they cross at a nice angle? Well, what these numbers are on this grid Going out from the center, it tells you the altitude of the star. And going around the circle, it tells you the azimuth, right? In other words, it tells you where to point your sextant and what to set it at ahead of time. So if you can find the LHA and you find Arcturus, you point your sextant in that direction, and you set it up for that altitude, look in that direction, and there's a star right in your field of view. Then you finish bringing it down to the horizon, click your stopwatch, and you got it, okay? Then after that, after you write that all down and everything, get everything set back up again, then you do Polaris, or you do Polaris first, and then you do Arcturus, whichever, it doesn't matter. But now you have 2 lines of position, and you can get a fix. So you don't have to worry about advancing your line of position along your course and speed. Okay, is all that making sense? All right, so here's what we're gonna do. Let's start off saying this is earlier today, okay? And we're going to do our twilight calculation for August 28th, sunset twilight, north 35 degrees as you look at it in the almanac, because that's the closest one. So go to the page today, and you're going to find the 2 twilight times, civil twilight and nautical twilight, for our latitude on that day. Okay, so can someone tell me?
You want to use 30 or 35?
35. We'll go with 35. We're slightly closer to that, so we'll go with 35. It's also what I worked out, so I don't want to confuse the issue. So you'll see 2 numbers. Yes, Margaret? Okay, so what we're doing is, first of all, we're predicting twilight. Hasn't happened yet, but we're saying we did this earlier in the day, and we're setting ourselves up for a couple star shots. So we're going to predict twilight for today, August 28th, 2024. It's evening, it's sunset twilight. So we go to August 28th, and we find civil twilight and then nautical twilight on August 28th.
You say for sunset?
Not sunset, twilight. Sunset is another one of those columns. Oh, it's the evening one, yes, sunset as opposed to sunrise, right? Because it'll give you sunset too. I'm sorry, I thought that might be what you're asking. But yeah, we don't care. We care about sunset if we want to be out with a cocktail looking for the green flash. That's what we really need to know. But if we want to know twilight, it happens a little bit after that.
1856.
That's right, very good. So the beginning of civil twilight is 1856, and then nautical twilight is what? 1927. Okay. Now, these are GMT times,
Wait.
right? You're not getting that?
No.
Okay.
August 28th?
August 28th.
Okay, so I'm looking here at 35 on sunset.
There's like 2 of them. There's
I got
one here
1805 and
one here.
1834.
Okay, all right, so we got a source of confusion. All right, let's see if I can help that out some. All right, so we're looking at August 28th. Okay. And
okay.
we're looking at twilight.
I'm
for
sorry,
sunset.
I'm below the equator.
Oh, okay.
35 degrees below the equator.
Okay, so we're north 35 and on
Thank you. Sorry.
Okay, some other people had some issues with that too, though. Does everybody see what we're looking at? 18 hours, 56 minutes? Yeah.
Oh, I see. One's in the morning and one's the evening. I got it.
Right.
I got it.
1856, and it's easy to confuse and accidentally read the sunset time, which is not what we're looking for. Okay.
1857.
Okay, so we do the little gyration that we do to convert arc to time. We're at about 117.25 degrees, and we know from past experience that translates to 7 hours and 49 minutes. Well, why bother adding the 7 only to subtract it for our time zone? Let's just add the 49 minutes in each case, right? So if we do that, we end up, I think, with the local mean time here of civil twilight as 19 hours and 45 minutes and 20 hours and 16 minutes being the nautical time. Does that make sense to everybody?
Don't you have to account for the day change?
Well, we are going to have to do that because we're just talking local mean time at the moment, and we're doing this prediction because we're probably going by the time that's on our watch. But of course, that local mean time, if we add 7, it gets us into August 29th. and we're going to have to deal with that too. But for the time being, looking at the clock that's on the wall, likely as not, or what's on our wrist, these are the times we're going to want to be up and shooting by just for predictive purposes. Now we don't have to be up there right at the crack of 19 hours and 45 minutes, though, right?
Yeah.
So we can be up there sometime during that period, okay? So, what we need to do now, though, for predictive purposes, we need to do what John just suggested. We need to translate that into GMT. So now, if we take those numbers, and let's just say, you know, we're going to start shooting our first star 5 minutes after the official twilight. So official twilight was at 19 hours and 45 minutes. We're going to shoot that first star at 19 hours and 50 minutes, and let's say that's going to be Arcturus, like we talked about. So at 19 hours and 50 minutes, when we expect to shoot that, we have to add that 7 degrees of difference for our time zone, and that gets us to 26 hours, 50 minutes. But of course, there's not 26 hours in a day. You won't find this problem for morning sites either, because you're always going to be in the same day, at least in our part of the world. So, but 26 hours and 50 minutes really translates to 2 hours and 50 minutes on August the 29th. So that's the GMT date, as well as the GMT time, okay? So that's what we're going to be trying to find Arcturus on our Starfinder. So what we need to do to use the Starfinder, we need to find the LHA of Aries, and to do that, we've got to do the normal thing. We've got to find the GHA of Aries for the day and the hour, to which we add the minutes and seconds, okay? And then from that, we subtract an assumed longitude to get an LHA. So if you look for August 29th, at 2 hours and 50 minutes, for the day and the hour of GHA Aries, so go to the 29th, and instead of going to the sun, which is where you've been used to going, go to the extreme right of the page to Aries. So on the 29th, at 2 hours, what's the GHA of Aries?
7 degrees,
7 degrees,
46.5.
46.5 minutes, okay? All right, now we do just what we did before with the sun. That's the day and the hour, so we have an additional 50 minutes, don't we? So we go to the 50-minute page, back in the gray pages, right? Or shaded pages. We go to 50 minutes even, because that's when we're going to shoot, or we're going to aim for anyway, and it's 50 minutes, 00 seconds, and the columns there are, first column is sun and planets, then Aries, and then the moon. So if we look at the Aries column at exactly 50 minutes, what number do we get? 32. Yeah, that was, you're reading what I got. If you look at Aries,
What page is this one?
it's on the page for 50 minutes. In the gray pages, you know, for the minutes and seconds.
It's in the index on page 27.
Oh yeah, it's Roman numerals 27, if you want to look at that.
So go further back.
So for Aries, we get 12 degrees, 32.1 minutes. Everyone see that? Okay,
Oh, there we go.
so when we add that, we get a GHA of Aries of 12 degrees. I got it anyway. Oh, wait a minute. I got 19 degrees, 78.6 minutes. And of course, you can't have 78.6 minutes, so 19 degrees, 78.6 actually becomes 20 degrees, 18.6, doesn't it? So the GHA of Aries is 20 degrees, 18.6 minutes, unless somebody got something else. Okay, well, remember what we got to do. We've got to have an LHA of Aries, don't we? Which means we've got to subtract an assumed longitude that ends in a whole number from, from that number. Well, you can't subtract 117 degrees from 20 degrees. So what you do is, when you're confronted with that problem, just add 360 to it, right? You go around the circle and you're back to the same spot. So you take that 20 degrees, 18.6 minutes, and you add 360 degrees to it. Okay?
So 380 minus.
It's 380, 18.6, minus 117, 18.6. Okay, so our assumed longitude is going to be 117, 18.6 minutes. So that we end up with that whole number for LHA, which, can anyone tell me what that is? What happens if you subtract our assumed longitude of 117, 18.6 from 380 degrees, 18.6? What is it?
263.
263, that is our LHA. So, what we do,
It's local hour angle for Aries, right?
local hour angle area, so 263. So, I'm going to take this disc. So you can see it. There's a bit of a lag time on this, and I'm moving this around. To 263. So this arrow is on. This arrow is now on 263. Okay. Now this is an old Starfighter. It's a bit faded, so I've got to look closely. I have to see which one of these guys is Arcturus, so I can find that out. Arcturus is this one right here. Okay. So that one right there, it is on an altitude of about, I want to say 45 degrees altitude, and the ZN is about 262 degrees ZN. Okay, so 45 degrees, actually 43 degrees, I think, and 262 degrees. So we set our sextant up for that when it comes time to do it, to 43 degrees, and we look over to 260 degrees when twilight comes, and Arcturus should be right in our telescope, okay? Without having to find it using a map or anything else. So, what I'm going to do is I'm going to say, okay, well, here's what we did. We shot it. And what it turned out to be was, this was on August 28, 2024. You're going to work this out, guys, and you're going to plot it. The height of eye was 6 feet. Okay, Arcturus, for Arcturus, the HS was actually 45 degrees, 12.5 minutes. Okay, so the dip is going to be the normal dip, but now for the main correction, it's not going to be for the sun, it's going to be for stars. So if you look over on that page that we normally get the corrections to correct the sextant, and you look at April to September, oh, first, never mind, don't worry about April to September, it's not the same, or it's stars and planets. You first correct the sextant for dip, right, at 6 feet, and then you take that number and you bracket it at apparent altitude just like you did for the sun, and it gives you a correction. Okay? So make sure you get the number from the stars and planets, not from the sun. And then other than that, a couple other differences I'm going to tell you is that you start off with I'm going to give you the local mean time was 19 hours and 50 minutes. That's when we started the stopwatch, to which you add 2 minutes, 12 seconds, which gives you, this is local time, 19 hours, 52 minutes, 12 seconds, add 7 for the time zone, and that means you've got 26 hours, 52 minutes, 12 seconds, or 2 hours, 52 minutes, 12 seconds on August 29th. Okay, that was your GMT on August 29th. Okay, let's start off with the local mean time. We started our stopwatch at 19 hours and 50 minutes, like we wanted to do. And then we set our sextant up for the altitude and azimuth, and we looked through our sextant, and we found the HS was 45 degrees, 12.5 minutes. And then right when that star hit the horizon, we clicked our stopwatch, and that was 2 minutes and 12 seconds. That gives us a local mean time for the shot of 19 hours, 52 minutes, and 12 seconds. But when we add the time zone of +7 in there, that gives us 26 hours, 52 minutes, 12 seconds. Or, in other words, 2 hours, 52 minutes, and 12 seconds on August 29th. Okay? All right, so what we have to do now is we have to do GHA of Aries and have to find out what that is, which we kind of just did a minute ago. All right, find the GHA of Aries for that day, hour, minute, and second. And then we go to August 29th. Okay, we're going to go to August 29th on the white pages. And on the page for August 28th, 29th, and 30th, Wednesday, Thursday, and Friday, if you look at the column, the rightmost column of the leftmost page, you'll see stars, and they're arranged alphabetically. You drop down to where you find Arcturus, and it gives you the sidereal hour angle of Arcturus. You add that to the local hour, to the GHA of Aries to find the GHA of Arcturus. And it also gives you the declination of Arcturus. You don't have to worry about a little D factor here. The declination is not changing hardly at all. So you just write down that you'll use the SHA of Arcturus there and the declination of Arcturus. But again, that SHA is the SHA of Arcturus added to the GHA of Aries, but you still need the minutes and seconds because we didn't do it on the even day and hour. We had an additional 52 minutes, 12 seconds. So you'll want to go to the 52-minute page, back in the gray pages again, right? And you go to the 52-minute page, and you'll see the three columns: Sun, Planet, Aries, and Moon. So you drop down go to the 52-degree column, and you drop down 12 seconds, and then you write down how much this sidereal hour angle has increased in those 12 seconds, 52 minutes and 12 seconds, and you add that. So the combination of GHA of Aries, sidereal hour angle of Arcturus, plus the minutes and seconds gives you a GHA for Arcturus. And when you get that, now you know what assumed longitude you're going to have, that you're going to subtract. And for your assumed latitude, just as we've always been doing, just use 33 degrees. Okay? All right, everybody, go ahead and work that through. Okay? It's really no different than the sun sites you've been doing, that's all. It's just you're working with slightly different sets of entries, that's all. So give it a try. Yep. So I'm just going to go around and help you out here. We're 5 minutes into that period. Actually, 7 minutes into that period. Okay. So the prediction, what you're doing is sort of selective insight you're predicting. So the validity up there with your sextant. And it also allows you to predict using the Starfinder what to set up your sextant. Well, right? And once you've done that, now it's actually being decided. Trying to determine something studying the median of the GHA concerns, and then now in seconds, the median of the GHA errors.
Right. What that is.
Find the GHA of areas by finding, first of all, the GHA of Arcturus, I'm sorry. Find the GHA of Aries, add to it, so here are our angle for Arcturus. Find the you have against. That gives you GHA. Okay, is that making sense? Anybody like any more help?
Okay, so I'm at 2 hours, 52 minutes. So I wrote down the SHA of Arcturus, 145, and now I want to go to the Aries column here for 2 hours.
Right.
And write down that 746.
Right.
And add that to that, plus then the minutes.
Well, let's back up just a little bit. So you are on the day and the hour, right? So
Yep.
you're August 29th.
Yep.
All right, so the day and the hour for Aries.
Yep. That's 7 degrees. And 46.5.
Yep.
Okay. And then I want to go to the back and add that 52 degrees for the 20 minutes.
Right.
Well, actually,
Right. Well, what I would do another thing while you're on that page, just to save time, is look up Arcturus.
Yes, I have that
Okay,
down.
so write down-
Yes,
so write
the
down-
SHA, I've written
Write down that, and while you're at it,
Explanation.
there you go. Yeah, that saves you some time flipping back and forth.
Okay.
All right, if you have those two numbers though, when you finally get the actual Arcturus GHA with the minutes also added to it,
Uh-huh.
and then you add the SHA of Arcturus to that.
Yeah.
If it's over 360, you just
that
subtract
helps.
360.
Right.
And don't worry about the date though, because
Right.
basically you just
Well, keep in mind, if it's over 360, just keep in mind what you're going to do to that number. You're going to subtract your assumed longitude from it.
What?
Well, to get a local hour angle, which
Oh.
is what you need for the 249 tables, you're going to subtract your assumed longitude from it. So if it's over 360, you know, you got something to subtract the longitude from, right? If you were doing this in the morning, you'd have to add 360 to it to get a number large enough to subtract your longitude from. That make sense? So remember, the LHA of something is the local hour angle.
This is the difference.
It's the GHA of the thing minus your assumed longitude.
Yeah.
So once you found the GHA of Arcturus, in this case, it's more than 360, so you just subtract your assumed longitude from it to end up with a whole number LHA. All right? If we were doing this in the morning, you'd probably have a little GHA. You need to add 360 to it to get a big enough number to subtract our assumed longitude from and end up with a positive number.
Okay, to get the difference between the two.
Right.
Okay.
Right. So
Put up your numbers so I can see it.
put up some numbers here.
I got anywhere.
Okay, let's try that. Let me put some numbers up here.
Well, we have to give the SHA.
So probably your USB port.
Oh, that's interfering with navigation here.
I'm not sure why, because there should be a USB port right now connecting those two.
Yeah. Hang on a second. Okay, so that's still. How do we get rid of that?
I don't know. There's no USB port connected to it. It's not a computer.
Oh, that's really weird, and it's not even a computer at this point.
That was the source.
Maybe so. Yeah.
Nope, that didn't do it. That should do it.
What if we turned it off and turned it on again?
Hit with a hammer.
It's right here. Sure. Try that.
Just reset it. So you hit it twice. No, only just hold it down for a few seconds. There, it was a few seconds.
But it's still saying that. So
It's this. There's a
That guy.
USB port on the thing. Okay, let's turn it back on.
So then I suspect what we need to do is
And-
restart this one.
See if it resets itself.
So that gives
It'll
us.
take a little while to get back going again.
Yeah. I walked out this morning without my projector. That was the problem. Okay.
Okay, it's gone now.
for-
Oh, wait.
We're gonna use that.
Honesty still corrected. Okay, well that should be fine.
Okay, wait, that's gone out.
Okay, so well before this messes up again, I'm going to run through this with you. Okay, so it was August 28th, 2024. Arcturus, height of eye 6 feet. The HS was 45 degrees, 12.5 minutes. 6 feet gives us a dip correction of minus 2.4, right? So that gives, all right, and then we do that and it gives us 45 degrees, 10.1 minutes. Then the main correction was minus 1.0, looking at stars and planets, and that gives us an HO of 45 degrees, 9.1 minutes. Now the time we took it was, the local mean time was 19 hours, 50 minutes. That's when we started the stopwatch. When we actually took the site, it was 2 minutes and 12 seconds later. And that gives us a local mean time of 19 hours, 52 minutes, 12 seconds. With a time zone factor, that's 26 hours, 52 minutes, 12 seconds. And that gives us a GMT of 2 hours, 52 minutes, 12 seconds on August the 29th. Okay? So we needed to find the GHA of Aries, Greenwich hour angle. So when we looked in the white pages for August 29th at 2 hours, we got 7 degrees, 46.5 minutes. Okay, but we weren't at the even 2 hours. There was another 52 minutes and 12 seconds which elapsed but when we took the site, and that minutes and seconds correction from the shaded pages under the column Aries was 13 degrees, 5.1 minutes. So the GHA of Aries, which is this arbitrary point in the sky, it's kind of like the Greenwich Meridian, it was 20 degrees, 51.6 minutes. Okay, now we need to know the GHA of Arcturus though, because that's the star we shot. So we looked on the daily page, August 29th, for Arcturus, and we found the GHA of Arcturus was 145 degrees, 48.3 minutes. We added that to the GHA of Aries, which gives us 165 degrees, 99.9 minutes. You can't have 99.9 minutes, so that is 166 degrees, 39.9 minutes. Right? Okay. So that means, and while we were at it, we wrote down our declination for Arcturus, which was 19 degrees, 3.4 minutes. Okay? And while we were at it, we made an assumed latitude, because it's what we're doing, we're in this part of the world, it's 33 degrees north. That's the whole number latitude we need for the 249 tables. So then, we did just what we do for the sun. We made up an assumed longitude that's going to give us a whole number when we subtract it from the GHA of Arcturus. So we know, we're somewhere around 117, 15 or so. We picked an assumed longitude of 117 degrees, 39.9 minutes, which gave us an LHA for Arcturus of 49 degrees. Okay? So now we've got what we need to go into the 249 tables, right? So we've got a declination of 19 degrees, which is more declination than we've been dealing with. So we go to the latitude 33 degrees page. The declination of Aries is north, so it's the same name as latitude. So we look at 15 to 29 degrees page. So north 19, okay, so we look for in the 19 degrees column. We've got an extra 5.4 minutes to deal with, but we're just doing the 19 degrees and at latitude 33 and an LHA of 49 degrees. And we also write down a little d from that page of plus 28, which means each additional degree of declination gives us another 28 minutes of HC. So when we cross-index the 19 degrees of declination with the 49 degrees of LHA, we get 45 degrees, 4 minutes, okay, for an HC. Now, it's not exactly 19 degrees, it's 19 degrees, 3.4 minutes. So when we cross-index that 3.4, round it to 3, and we cross-index that with 28, that gives us 1 minute of correction. So that gives us an HC of 45 degrees, 5 minutes, okay? Now, when we did our sextant HS, corrected for dip, then the main correction for the star, we end up with 45 degrees, 9.1 minutes, which is the larger of the two. So we subtract our HC from the HO. So from 45 degrees, 9.1 minutes, we subtract 48 degrees, 0.5 minutes, and we end up with an intercept of 4.1 miles towards the star. The star direction was 96. The Z from the 249 page was 96. LHA is less than 180. So the number we're really looking for is 360 minus 96, which gives us what? Let me read my own handwriting. 264 degrees, okay, of ZN. So we were looking kind of to the west, just a little bit to the south or west, right? 264 degrees is ZN. All right? So, with that, we have what we need to plot that line of position. So we go to latitude 33 degrees, right? Latitude 33 degrees. We go to our assumed longitude 117.39.9. That's our starting position. That's our assumed position, not our DR position, our assumed position. We draw a line on 264 degrees true, right? So we draw that line, that's the direction to Arcturus, and we come out 4.1 degrees and we strike off a perpendicular. Okay? Why don't you guys go ahead and plot that? You got something to plot that on.
The ZN is 244?
264.
264.
Yeah, 264. Sorry, Mike. I do this fast and I can't even read my own handwriting most of the time. Hang on a second. I got it as 49. Is that not right? If we subtract 117 from 166, what does that give us? Okay, so it's 49.
I don't think your HC is correct.
Okay, so let's start with, well, it might not be because I was doing it fast. So let's go to the latitude 33 page. Declination same as latitude. And let's go to the 15 to 29 degrees page of the 6 pages there. And we cross-index 19 degrees of declination with 49 degrees of LHA. And what do we get for an HC? Oh, well, I'm wrong then. So it's 44.14. They're tiny little numbers, so I guess I blew that one. Okay, so 44.14. All right, let me look and see if there's something awry with my page.
Oh, there it is again. Should I do it now or wait?
Hang on just a second. Let me look this up. Yeah, I got 44.14. So let me make a correction here. It's always a problem when you just make these things up. So HC is 44 degrees, 14 minutes. Okay? Everybody okay with that?
Yeah.
Okay, so that gives us 44 degrees and 15 minutes. So now this one is wrong. So we start off with an HO of 45 degrees, 9.1, and we subtract HC, 44 degrees, 15 minutes. Let's make this 44 degrees, 69 minutes. So 69 minus 15 is 54, and the HO is bigger, so it's towards. Okay? So if I was going out to just make up an HS, I would have picked another number closer. There you go, because I worked this backward. So what you want to do is go to that spot that you're going to plot, and you're looking at your assumed latitude of 33.
Bring it back up since you're off screen. I
okay.
rebooted though because it was doing the whole thing again.
Okay. It'll come up shortly. Okay. So it's assumed latitude 33 degrees north, Assume longitude 117.39.9. So that's your starting spot. Did I get that right for the Z? Was that 96 or was that another wrong too? 95. 95. Let's make that 95. And this makes this 265, doesn't it? .265 is the Z-end. So now you have what you need to plot it. And move it out 54 miles on that line. That's a long, and you're using the San Diego Santa Rosa Island chart, that's a long way. That's almost an entire degree, so. It may go off the chart. So if you're using a universal plotting sheet, you got more coverage, more surface area, it's easier to do.
And so the intercept then is toward, we're not using the sun.
It's towards Arcturus. It's out towards Arcturus, starting at that 33 degrees, 117.39, almost due west, to 265 degrees, a total of 54 miles. 54 miles towards the west. So quite a ways, actually. Yes? Question?
If you already know where Arcturus is, do you have to go through that whole...
If I missed it, what was the question one more time?
If you already know where Arcturus is, you're familiar with Arcturus, where it is, do you have to go through the Starfinder?
Well, if you already know where Arcturus is and you can find it, yeah, you don't have to. You can, like I said, you can do the several things we talked about. You can just find it, look at it, bring it down the horizon. Sometimes it's easier to bring the horizon up to Arcturus. Or if the thing is, what happens though is it starts to get, there's sunlight out there, it's light, like it is now. You don't see the stars at this point. When they start to appear, you don't see the whole sky to orient yourself very well. You're just seeing these little points of light. So it's helpful to know how high what to set your sextant ahead of time and where to aim it. All right, there won't be another star there. If you see a star, that's the one that the Starfinder has predicted. Okay, so just take a few minutes and plot that out, and then we're going to do not another one of these, but a similar thing to actually get a position. There's no Polaris?
No, there isn't. And the stars here.
Oh, there's not there, no. No. You have to go to the Polaris page.
Oh, there's a special page for it.
Yes, so remember we talked about that last time? The Polaris tables? Okay, you're going to find them on page 2, beginning on page 274. 3 pages, 274, 275, and 276 in this Blue Nautical Almanac. Yeah, Polaris is not one of the stars listed in that tally there. It's got its own special case. And remember, you go across the top of the page with LHA of Aries, which is why we calculate that. Yeah, and then you drop down and then you look at the formula at the bottom. Whatever your HO is, minus a degree, plus A sub 1, A sub 2, A sub 3. Staying in the same LHA column all the way down.
What do the different A sub numbers do?
They're just the corrections you add from each portion of the Polaris tables.
Right, is Aries just an arbitrary location, region?
Yeah, that's a good question. So is Aries arbitrary? It's kind of arbitrary in the same way the Greenwich Meridian is. So it's a point in the sky that crosses, Aries is the ram, it's a constellation.
Mm-hmm.
It crosses the star that defines, I think, the leftmost of the horns of the ram. It's just, they could have picked any spot.
Okay.
That's what they picked.
I just like to know where it is, though. That way, when I look at LHA, I can like,
yeah.
okay,
Well,
that
you-
looks about right.
So you'd have to
You look
find-
at between that and the star you're trying to find.
Yeah, you'd have to find the constellation Aries, you know,
Yeah.
first of all, and then you can find it from that. And I'm not sure which star that is, actually.
I just figure if you do that, then you look at it, okay, well, it's about, okay, so you know if you're in
Yeah.
the right ballpark.
Yeah, that would help, yeah.
But is that because Aries is always visible at night?
No, it's because they had to pick something.
Why didn't they just pick a star?
What I'm saying is that because isn't Aries sometimes on the opposite side of the Earth?
Right, you might not see it. It doesn't matter though, because you really are looking at the local hour angle of Aries. The only reason that they require that you find the GH of Aries, it's the reference point. It's like you also can't see Greenwich either. Doesn't matter.
Yeah.
You know, you're so far along from Greenwich. So why did they pick a star?
It seems like that'd be easier. That way, you actually, as a reference point to work all the other problems off of.
They did pick a star. So the first point of Aries is a star. It's a star in the constellation Aries, from which everything else is related to. Similar to, they picked the Greenwich because that's where the observatory was.
Is it a decent magnitude star where you can see it generally at twilight? After twilight?
I don't know. Maybe. I've never once used it in the way that you're describing. So it's a good question. I don't really know. It's really only an arbitrary place in the sky that was picked because they had to pick
So nobody
something.
cares. They just basically use the numbers and they'll actually
Right.
kind of get an idea by looking at the angle.
Right. No, it's
I'm sure the
not.
Polynesians would have, though.
What's that?
I'm sure the Polynesians would have.
Yeah, well, they had it in the sky like that. But yeah, that's all it is. It's just an arbitrary spot on the celestial sphere.
Okay.
But I would think that most of the Polynesian experience with the sky is in the southern hemisphere.
Most of it is.
And
So
therefore they didn't have
Might not be able to see
more
it.
of understanding that one star.
well, also they did it. Their whole system of wayfinding, understanding how it all worked, is alien to the way we do it. It wasn't. When we're doing celestial navigation, we're employing an absolute reference system, which is completely an opposite to what
I
they did.
understand that, but
Yeah.
what I'm saying is we had the luxury of that to build upon. They did not.
Yeah, that's true. That's true. But again, Aries wasn't exactly a luxury. It's just a spot they picked. There wasn't anything particularly great
I'm
about
saying,
it.
I'm talking about Polaris. And that it's a
Oh, if you're
more
talking
of a
about-
reference.
Yeah, if you're talking about Polaris, that's different than Aries. So if we went to
Yeah.
switch the subject to that, that is true. But again, we started figuring out how to do this before Polaris was a North Star, right? It wasn't
It
useful.
wasn't there yet.
And for hundreds and hundreds of years, there was no North Star for any mariners to use. It was too far away because of that wobble that the Earth does. So it's an advantage, but it's a temporary one.
So just wanted something like along the ecliptic? So that basically kind of be general, so
Yeah,
it's
probably.
mapped around easily?
It might be along the ecliptic. I actually don't know where it's at.
I would assume it'd be somewhere along there, within the
I would
average of the
think.
precession.
Yeah, I would think so. Again, never used it, so I just haven't considered that.
Okay, so I'm on the Polaris page.
Right.
And I found the right column for LHA.
Yep.
264. But I kind of gone fuzzy about what are these numbers.
So what you do, okay, so 264 is the column we want.
Yep.
Okay, so let me take my glasses off here. So you are looking at the column that goes from 260 to 269.
Yeah.
Okay, so you start with an HO. If you look at the formula down here, latitude equals the HO minus the degree plus the A sub 0, A sub 1, A sub 2. So start with the HO, you subtract a degree from it to begin with.
So my HO's 32.
Yeah, I did. I wrote whatever you wrote down.
Yeah.
So you subtract a degree, and then in this column, 260 to 269, all right?
Yeah.
We're at 264, I believe, is that right?
Yes.
Okay, so you drop down to where it says 4, so it goes 0 to 10.
Uh-huh.
So at 4, in that column, you get 1 degree, 28.7 minutes.
Where did I pick that 4 from?
Well, it's 264. See, that's the most confusing part about this table, is it gives you a range across the
okay.
top.
That was
It's
your
an
question,
actual
was
number.
260, that makes 264.
Right. It's only giving you a range across the top.
Okay.
You have to find the actual number. Okay, so that doesn't happen elsewhere, just there.
Okay.
So you come down to 264, and then you look at the correction, which is
Okay.
1 degree, I believe it's 28.7.
So I take my 32 first and then minus 1 degree.
Minus 1 degree,
Okay.
and then add back in 1 degree, 20.7. And then you drop down.
So minus 1. 16.7, 264. So 264. So it's 1 degree. 28.7.
Okay, then you stay in the same column. And we're closest to latitude 30, and that gives you 0.5, which you add. And then you drop down to the next section to August, which gives you a correction of 0.9 in the same column.
Yep. Okay. I think I had that same question last week. Well, how does that column work again?
Yeah, that's the one that everybody's puzzled on.
That one is-
We just assumed that if you have within that range, use the top number.
Yeah.
No, you in that range, you had to go down to the column and see which one within the range.
That's right. It is confusing. That it's one of those things they do to economize the number of pages that they want to put into the book. So,
16.7.
okay, we're going to look at this now. This is what we just worked out. Unfortunately, we got this damn thing in the way, so. Thanks, Eric. We'll get this going again. So.
I'll only get it fresh for about 5 minutes and it
Yeah,
comes out.
yeah, and then we're done. We're done with this later.
Okay.
I think, after this.
Okay.
Okay, so in doing Polaris, we have a local mean time of 19 hours, 56 minutes, 12 seconds. We added the 7 hours for our time zone, which gives us 26 hours, 56 minutes, 12 seconds, which is really 2 hours, 56 minutes, 12 seconds on August 29th. We had an HS of 32 degrees, 20.6 minutes. So our dip correction for 6 feet was minus 2.4. So we subtracted that from the HS, which gave us 32 degrees, 18.2 minutes. And then our main correction from the stars and planets column of the correction to correct the sextant tables is minus 1.5, which gives us an HO of 32 degrees, 16.7 minutes. Okay? So now, to use those Polaris tables, we need to know the GHA of Aries. So GHA of Aries for the day and the hour was 7 degrees, 46.5 minutes. And then for those extra minutes and seconds, the 56 minutes and 12 seconds, that was another 14 degrees, 5.3 minutes, which gives us a GHA of Aries of 21 degrees, 51.8 minutes. Now, we're going to have to subtract our longitude from that to end up with a whole number, which is our LHA of Aries. So we don't want to end up with a negative number, so we just add 360 to 21, which is what we always do if we got to subtract a bigger number from a smaller number. And we end up with 381 degrees, 51.8 minutes. Now, we're not going to plot an assumed longitude here. We're not going to worry about it, but we still do need that LHA of Aries. So we're just going to make up an assumed longitude of 117 degrees, 51.8 minutes, and that gives us a LHA Aries of 264 degrees. That allows us to go to the Polaris tables. So we go to the Polaris tables, we look under the range 260 to 270, and instead of just taking the top number, we drop down to 264, all right? And, well, first of all, before we do that, sorry, I got ahead of myself. Before we do that, we subtract 1 degree from the HO, and that gives us 31 degrees, 16.7 minutes. Now we add the A sub 0, which is the 264, which is that little confusing part because we've got to drop down to 264, and I made that out to be 1 degree, 28.7 minutes. And that you add. And then you also add A sub 1 for the latitude, which is half a degree, and then you add A sub 2 for the month of August, which is 0.9. So all those things put together gives you 32 degrees, 46.8 minutes, which is the latitude. So if you take that latitude and you cross that latitude with the line you drew for Arcturus, that's actually our position. Okay? So anyway, so there we are. Okay, so look at that, try to work it out further. So I'm going to tell you that your homework next time is not going to be that easy physically to do, because what I want you to do is do what we just did. I want you to actually find Arcturus and shoot it, and find Polaris and shoot it. But if you note, in the afternoon, evening sky, it's pretty clouded over. So we may not be able to make it before next time, but try and give it your best shot. If all you see is Polaris, just do Polaris, okay? Now, how many of you, just out of curiosity, have Volume 1, the selected stars? Raise your hand if you have Volume 1. Okay. If you have it, bring it with you, because it's a really handy thing. It's easier than using that star finder. And there's a special technique, clicking in positions, using Volume 1. I really don't want to force people to buy another $30 thing, you know, which is what it would be if you ordered it on Amazon. You can have it by next week. So what I'll try and do is pick the page out that we're going to get and bring that in. But if you like the way, we're going to figure out a way to do a star shot pretty rapidly and easy. And we'll need the 241 Volume 1 publication is helpful to that.
So we want to shoot Arcturus?
Yeah, shoot Arcturus, because it's easy to find.
Okay.
So Arcturus and Polaris.
Okay.
And if you or either, whichever one you can see. Okay? All right? Got that, everybody?
Are they in a position that from the coast-wise, you could get a horizon on them?
Well,
It'd be hard to get Polaris.
Yeah, you're going due north, so that's not going to be easy to do. So just do the best you can.
Okay.
Yeah. There's not many places here, you know, you have to get out to sea to actually shoot due north and get something.
Okay.
You might be able to do that from La Jolla Cove, perhaps,
Okay.
you know, but not too many places. But in this instance, just do your best to get a horizon. You know, it's not going to be perfect, but that's okay. So go ahead and do that and work it out and work out the site and get a position. It won't be where we're actually at, but, you know, it'll probably be better than the thing I just made up out of plain air here. So, okay? Okay, so bring table 1 if you got it, and I'll try and have that
Table
up.
1 for site reduction table?
Yeah, Volume 1. Volume 1.
Volume 1.
And they come in epochs. They're only good for 10 years. So I think this one is 2020 to 2030 or something like that. Okay? So if you ordered one, you'd get the right epoch. You know, they probably also have them in Seabreeze, but I'm going to bring in the page we need, okay, for everybody as a handout. Alrighty? So try and do a position by Polaris, the best you can do, and by Arcturus, okay? And we are going to take a bit of a break and come back in 5 minutes, okay?
Is next week Tuesday or still Wednesday?
Well, I think it's Tuesday. Next week I'm not going to be here on Wednesday. So let me just confirm that. So next week, instead of Wednesday the 4th, it will be Tuesday the 3rd, same time. All right? Okay. Just out of curiosity, is there anybody that wants to stay around after this for any special help or anything? It still makes for a long day, I know.
I have a quick question though, but when do you go on break?
Okay, all right. Yeah, all right, very good. Okay, everybody, we'll see you back in just 5 minutes. Oh, thank you. I'm passing up my stock. Over the last couple of nights, last few times we were talking about nautical disasters and how they were encouraging all these efforts to solve the longitude problem. And there were it was a multi-dimensional thing, actually, because you were actually doing several things. You're pitting a solution as to making prizes or rewards for finding a problem. So it was like the economy was in play, but there was also institutional approaches, so that there were institutions like the National Observatory. And this was the first time really this had happened in this way, and it kind of set the stage for a whole bunch of things like intellectual property. So for instance, someone is a university professor, they have a career researching some sort of phenomenon in physics like superconductivity, and say they make this great discovery after having worked for years in university labs at public expense. They quit their job as a professor, they do a startup, and now they're selling superconductors. So did they actually own that property even though they were supervising lab and generated that? Does the university own it because the university was subsidizing all their work by a grant? Who actually gets to own this stuff? And so when Newton and Halley, who needed Flamsteed's data to generate the tables for lunar distance, kept bugging him. He said, I'm not ready. And they finally got a hold of his data, and they published it. He was really ticked. His point of view was, I bought the instruments, even though I was on the public payroll. it was my observations, they were my instruments, that stuff belongs to me, not to you. I demand that you give all the published copies back. They did it. He went out with his own money and bought every copy he could find and burned them all. Okay? So again, a lot of those problems have still not quite been solved. They have, to a large extent, but intellectual property, who is it, who owns it between one nation and another, you know, what are the requirements for copyright and for that. And so all of this came to the fore for the first time once they started these sort of contrasting methods of problem solving. It was also the case that these institutions, by promoting navigation, were promoting also an understanding of the world and promoting almost a political philosophy in the age of absolutism. So Louis XIV, for instance, the Sun King, really did not like the Christian idea, the Ptolemaic idea of everything revolves around the earth, because he thought everything should revolve around him as the absolute monarch. And since his identity was a sun, he really liked the Copernican universe. And a lot of the institutional investment in this was subliminally, it appears, contrived to reinforce the authority of these absolutist states, which included Britain, it included France, and so forth. And so these institutions were physical manifestations of the authority of the monarch and the authority of the nation state, just as all of those embellishments on their great warships were also emblematic of their power and their authority, and just as these instruments that were being created, which were beautiful and intricate and mysterious and difficult to understand in excess, that was also an expression of national authority in an age of absolutism. So all of these things were interwoven, and so the creating these national awards for things was actually part of reinforcing what it meant to be a nation state and what the role and duties of the heads of nation states were. And so whenever these people were coming forward with solutions to these problems, they were typically, when they wrote books, they were dedicating them to the monarch, dedicating them to wealthier, well-to-do people whose patronage they wanted. So these things were definitely, these solutions and were definitely avenues for patronage and social standing, and it was one way for people that were really smart, that may not necessarily have been well-born, to increase their status and their wealth dramatically by conspicuous association with problem solving this way. Okay, so it was a pathway also for economic mobility, just as it was a pathway for the actual physical mobility of ships moving over the ocean. And likewise, navigation and the ability to learn it, absorb it, teach it, and everything else, again, that was how you got up to a position of authority in a maritime structure, as you had specialized knowledge that was absolutely essential to the prosecution of trade and the prosecution of warfare. So all of this thing combined, for the first time, really, were these specialized branches of knowledge were really important to people's ability to advance themselves, promote their careers, promote their political parties. And for the first time, really, in an organized fashion, science was key to that. And so that also elevated the stature of science, which was before this thought to be useless, just a useless exercise, or an area for dilettantes, actually ended up being reinforcing the political structure of these nation states, maritime and mercantile nation states, and reinforcing the careers of the people who followed either astronomy or science or navigation and so forth. So these things were all interwoven, so to a large degree, understanding the evolution of navigation is really understanding the evolution of science and of nation states also, because they were also intensely interwoven and resulted in all these people attempting to advance themselves through really, in many cases, totally crackpot ideas and bizarre notions of things. So they were also creating, since some of the things were about time, particularly longitude, there was a belief in clockwork universes, a whole belief of deism that proposed that, you know, God didn't take a day-to-day, didn't exert day-to-day influence on people's lives. They set the clock in motion, and then the clock just ran. Okay, and that's what existence was, that's what nature was the running of an ongoing clock that had been set in motion at the dawn of creation. And so the investigation of these phenomena and the investigation of what made them all work was an attempt to unravel the religious mysteries of the universe as well, and that also reinforced the social and political structure, gave the sense that, okay, it's not God deciding who got to be king versus some of the things. It was kings were God's anointed leaders and servants fulfilling his will by the result of, reinforced by all of this apparatus of philosophy and science and so forth. So they all work together. So this was the golden age of instruments in which people could also advance themselves by their creation. Campbell's sextant, as you see here, was accurate to 2 minutes, which was important because 2 minutes of error in the lunar distance problem generated an entire degree of error. Okay, so you had to be dead on the money when you were doing observations using lunar distance. Also, the mathematics involved was pretty inaccessible. In using Maskelyne's first set of tables, it took 4 hours to reduce a site. So you can imagine, we've been doing it 10 minutes or 20 minutes. It took 4 hours to do it.
I'm still
and
doing
plot it
4
out.
hours over here.
But it gets better. It gets better. I'm not making you do it his way. So, in any case. And so, it also, it was dangerous because you're looking at the sun and stuff like that. So, the advent of Hadley's quadrant and then the sextant were significant advances that allowed an increasing accuracy and also allowed people to pursue this without making themselves go blind. The quadrant was invented in 1734 by this guy named Hadley and also an American who lived in Philadelphia named John Godfrey. It's not clear who actually invented it. And when Newton died and they went through his papers, there was a description or a drawing of an instrument like this that actually predated the 1734 edition of 1734 invention of Hadley's quadrant. And the sextant in 1757 came into being, and sextants came into being because obviously nothing is higher in the sky than 90 degrees, so a quadrant just measured things to 90 degrees. But if you're going to measure the angle between the moon and certain stars in the background, you know, at an angle or horizontally, well, you need to measure more than 90 degrees. It's up to 60 degrees, hence the sextant. So ownership of a sextant, really, which was more expensive than a quadrant, the accuracy, level accuracy was much higher, what was required. Sextants were made out of brass. They were finely tooled instruments, as opposed to quadrants, which were typically made out of wood, usually ebony, with an ivory scale or an ivory arc. If you had a sextant, you're going to spend a lot of money on the thing. And you only did that if you knew how to use it. And so ownership of one of these things also suggested you were among the intellectual elite in your society, and certainly among mariners, if you knew how to use one of these things to solve lunar distance problems. Most people didn't. So, again, to go back a little bit in the story of last time with Anson's plight for Centurion, as he described it, to hit the island upon a meridian or hit the island upon a line. What they had to do is, first of all, there were 2 sources of error. One, as I don't know if you can make out on this map, to get to Juan Fernandez, they had to get around Cape Horn. Now there's a west-setting current, and as you shows them tacking back and forth until they finally cleared around Cape Horn, and then went in, darn it, it's the same thing showing up. Anyway, then they went into land to see Socorro Island, which there wasn't any other ships there to rendezvous, and then they found Juan Fernandez Island. Their problem was, by the time they got to Juan Fernandez Island, shown here, which you can barely see, they didn't know if they were east or west of it. Now, if they'd had some device that had been able to tell them their longitude, would that have solved the problem? Would they have been able to find themselves east or west to it? Alas, no, because that machine that could do that was part of an overall system that included charting. And in this period, the longitudes for South America were charted way too far to the east, right? So they could have actually been dead on their longitude and actually done the same thing. Now, on this map, between the coast of South America and Juan Fernandez Island, where they almost made Juan Fernandez, they were convinced they were to the west of it, turned to the east and sailed towards South America until they could see the Andes, and then turned west again and had to tack all the way to the west. 100 men died on the Centurion during that period. So it did make a fair bit of difference.
Why wouldn't they have just gone to land and got food?
Because that land was
would abandon the ship. Or not
well.
come back?
That's a good question. So at this time, Centurion.
What was the question?
The question was, why wouldn't they have just gone to South America to land and gotten food? Why not? Well, here's the thing. Admiral Pizarro's squadron had been destroyed by weather, but the Spanish activated another group of ships, warships, that were out looking for Anson. And they were ordered to take no prisoners. Anson did capture a ship where that information was revealed. Had they been captured by the Spanish, they were all going to get killed. There were going to be no survivors, no trial, nothing. Kill them all on the spot. So if they had just gone into land, it would have been in their weakened state, where they were all dying and of scurvy, and most of the crew left were children, that would have been it. So they really couldn't at that point, they couldn't actually confront anybody, any Spanish ships of any force. So they had to make it back to Juan Fernandez, and actually this delay did cause 100 people to die on the Centurion, but up until 3 or 4 days before they made Juan Fernandez, there was a powerful Spanish squadron there expecting them. And had they shown up sailing directly there, you would never have heard of Anson, because they were all been killed. So it was a pretty dangerous world. The Spanish took this really seriously, because this was threatening their whole empire. So anyway, ironically, that machine existed at this time. H1, Harrison's timekeeper, in 1737, actually made a voyage from England to Lisbon with Harrison's son on board, and kept the longitude within about 10 minutes or so, almost with perfect accuracy. This was 7 years before, or sorry, 5 years, because I think it was 1741 at this point. 5 years before Anson had that fatal episode going between South America and Juan Fernandez. But at that point, this was the only machine in the world that could do this. And ironically, it didn't work all that well on land. It worked pretty well if you took it to sea, you know. And its rate of going was irregular. But there was at this point a machine that existed that conceivably could have allowed them to find the longitude. Well, it's actually not true that it could find the longitude. When the award was established in 1714, during the reign of Queen Anne, if you recall, that was the award was established really at the provocation of this geometry teacher and Mr. William Whiston. And his idea for solving the problem was, let's see, I'm going to read the details. I think I did last time, but just in case I didn't, his scheme was to have ships arranged at fixed places throughout the Atlantic. They were going to fire a rocket designed to explode exactly 1 nautical mile in height. It would be visible for 85 to 100 miles from ships situated at 600-mile intervals. So every 600 miles, there would be one of these vessels firing rockets at regular intervals. How were they going to keep station? Well, they thought the Atlantic was only about 300 fathoms deep, when in fact the average depth of the Atlantic is about 2,000 fathoms. Okay, that's one problem. They also thought that the lower part, if you lowered down a sea anchor, that the ocean down at a certain depth was immovable, and that you could put a sea anchor out and that would keep the ship in the same place. Never mind that there's currents and things like that. So all these ships would be arranged 85 to 100 miles apart, firing these rockets. And if they're going to explode at 1 mile in altitude exactly, and you see it, at this time there were experiments being conducted on the speed of sound. So they did know the speed of sound. So you could time, if you had a fast enough, good enough clock, you could time the interval between the explosion and the sound. The reported stuff like when you hear lightning, you see the lightning, and then you hear the thunder later. Okay, so that timing, if you know the speed of sound, gives you the distance away. So by timing, you could tell the distance away from this particular ship, and the rockets would have their own characteristic. And then the combination of that and the bearing would give you your position. If not, you could cross-index 2 of them, and if you knew which ship it was, you could get the bearing from this spot and get your position that way. So this whole scheme would have taken no less than 7,175 ships to put it into effect, manned by 57,400 men. So it wasn't going to come cheap to do this, you know. And that didn't count intermediary vessels, and of course the depth of the ocean is about 2,000 fathoms. So, so it seemed like a totally crackpot, harebrained scheme. But if you think about it, okay, if you think of these ships as being on the surface of the ocean, in geosynchronous orbit at 0 degrees of altitude, or the rockets at 1 mile of altitude at geosynchronous orbit, it ain't that different from GPS when you get down to it, right? So crazy as it seems, but nonetheless, it's still, the basis of it is still some of the principles on which modern forms of navigation are based. So, however, at the time Whiston said, I've got this perfect plan to solve the problem, so put up a big award and I'll tell you what it is. So they did, and Newton was talked into it, not because he thought Whiston was had a realistic idea, because he thought Whiston always was a crackpot, but he thought that if he set up this award, it would set up another system for stimulating scientific advances, and that was through the possibility of acquiring personal wealth thereby. So it was kind of the socialized system of the National Observatory, the Royal Observatory, and then the capitalist system of getting paid for what you want to do. And they established that the award would be a 30-mile solution would get you 20,000 pounds. And so, but was Flamsteed or Newton or Halley, were they eligible for that 20,000 pound award if they had come up with a solution using the National Observatory? Nope. They were ineligible. They weren't going to get it. They had no chance of getting it because all of them were basically in the pay of the government. They were civil servants at this point. So they were not eligible to get it. Neither was Flamsteed, neither would Neville Maskelyne be when they finally came out with tables for lunar distance. As for the solutions themselves, Newton was pretty clear about that from the beginning. He said clockwork may be subservient to astronomy, but without astronomy, the longitude is not to be found. Exact instruments for keeping of time can be useful only for keeping the longitude while you have it. If you lose it, it can't be found again by such instruments. Nothing but astronomy suffices. So you might have a chronometer, but without reference to astronomy, you don't know if it really is accurate. And then you might have 2 or 3 chronometers and decide which one you like the best. You know, when Fitzroy sailed the Beagle on its circumnavigation with Darwin, he had 57 chronometers on the HMS Beagle. Right? With that, there's no way of telling which one of these damn things is the accurate one or not. You just had to average them. But what Newton was saying was a clock is a replica of the Earth's motion. Right? It's not the Earth's motion itself. It's just a replica of it. And how accurate and regular can that be is going to be determined how useful it really is. But if you don't have reference to astronomy, it's useless. So if someone comes up with a clockwork solution, are they ever going to win the prize of 20,000 pounds? No, they're ineligible. If you've read Dava Sobel's book, she says flat out at the end, Harrison was vindicated, he won the award for longitude. Harrison never won the longitude award. He couldn't. It was not. They weren't able to give it to him because his solution could not be relevant, independent of astronomy. Okay? So Whiston wasn't the only guy to come up with things. So the first guy to come up with a clockwork solution was a horologist named Jeremy Thacker, who in 1714 produced a device, and he wrote a book about it. And he said, the longitude examined, beginning with a short epistle to the longitudinarians and ending with a description of a smart, pretty machine of my own, which I am almost sure will do for the longitude and procure me the 20,000 pounds. Now, that was actually the title of his book, right? They had long titles in those days. So Thacker's machine, Thacker's clock really never was sufficient, but Thacker did something pretty cool. What did he call his machine? He called it the chronometer, right? Which is the name that has stuck ever since, the chronometer. There were other people that were projectors. John Ward, a year later, 1715. Henry Sully, who was a famous horologist, 1724 is a picture of his clock here. And the Frenchman Jean-Baptiste Dutertre, 1728. Two famous horologists at the time bent themselves to it, Thomas Tompion and George Graham, and they tended to rely on pendulum devices. And the problems with pendulums is if the ship's moving around, just like you saw with that quadrant, it messes it up. And also, pendulums have different periods depending on your latitude, right? And that wasn't perfectly understood, but that would throw them off in error. However, if you go into the Greenwich Observatory, into the octagonal room, right, which was the basis of the observatory, you'll see on the wall 2 large pendulum clocks. Those were built by Thomas Tompion in about the year 1710, and they have been running with fair accuracy ever since. So pretty cool when you look at those things and realize they have been running consistently. George Graham was on the longitude board, was a friend of Edmund Halley, and he was considered at the time England's foremost horologist. And England at the time was the center, London was the center of the universe for clockmaking, and actually for instruments of all kind. If I'm going to back this up just a little bit to this picture right here, what you see in the upper one is what's called Jesse Ramsden's dividing engine. It was designed and built in 1771. This particular one is in the Smithsonian. And it was one of the first precision machines designed to build other precision machines. From the dividing engine, you got sextants and quadrants and all kinds of astronomical objects that could be reproduced with fantastic accuracy using this machine, okay? At the time, by the latter part of the 18th century, there were 15 of these things in this one section of London doing nothing but pumping out instruments. So it was the center of the universe for this kind of instrument. It's the center of the universe for also clocks as well. So much so that the economist who invented the word capitalism and defined it and all, I'm drawing a blank on his name. That's why I should have notes. Come back to me in a minute or two. Anyway, it is the visible hand and so forth. In the first really true economics work where capitalism is defined, there are these various examples of how capitalism worked, and the clockwork industry in London was one of those that was foremost ones that were given. And the name will come to me. It's later in the day, I guess, so I'm losing my memory here. So back to this. So George Graham was the foremost horologist of his day, and if you wanted to make your name as a horologist and get people to want to buy your clocks and stuff, you pretty much had to have an endorsement by George Graham. So as it turns out, on a particular day, and I think it was 1730 or so, George Graham was woken up, George Graham was approached by this guy, John Harrison, from Yorkshire, who basically just showed up at his door and said, I've got an idea for a longitude machine, for a chronometer. Here's what I want to show it to you and tell me what you think. First of all, he showed up without an appointment, without ever notifying him, and Graham just started off like, you know, I have crazy people showing up at my door all the time. You know, could you just go away? But Harrison was persistent, and he revealed that he had several mechanisms of his invention that would make his clocks better than any others. And so, and he had actually made a living in Yorkshire making clocks for churches that were fantastically accurate, mostly made out of wooden pieces. Several of these things have survived, and they're really truly marvels of mechanical engineering. And it's also famous for one of the churches, his famous long case clock of 1726. To make these things work, he did, you know, there was a lot of inventions. The upper left picture are X-rays of some of his cogwheels, and they have weights and things inserted into them to balance them in certain ways. But they were all made out of lignum vitae, which is an oily wood, so it's self-lubricating. Harrison also invented roller pinion bearings, similar to roller bearings today used in all sorts of mechanical devices. The pendulums of the pendulum clocks people were using were problematic because they were made out of metal typically. That metal expanded and contracted ever so slightly with ambient temperature and changed the period of the pendulum. Harrison invented something called a gridiron pendulum made of dissimilar metals that had different coefficients of expansion and contraction, so they tended to cancel each other out, keeping the pendulum of a constant length and therefore its period of a constant time. Okay, so again, he goes into 1830 to London and knocks on Graham's door, and he said, Mr. Graham began, as I thought, very roughly with me, and which I had to have occasioned me to become rough too, so they apparently didn't get on well from the beginning. However, finally we got the ice broke. So they ended up, Graham said, you know, you might have something. Brought him in, had him explain his clock to him, and said, you know, you might have something. I tell you what you do. You take your clock and your designs, and you need to go see my friend, who was at that time the Astronomer Royal, the second Astronomer Royal, Edmund Halley. Just go see him here, write a note, tell him I sent you, and bye, I'm going to bed. So Harrison, you would have thought, would have waited till the next day. He went straight to Halley's house, knocked on the door, and this is like 2 in the morning, and Halley gets up, you know, what is this about? He says, I've got a clock for you, you know, and this is like 1 in the morning. Halley wasn't particularly more pleased to see this guy at that time of the morning than George Graham had been. But his initial impulse was to just kick him out, make him go away. They said, okay, come on in. And to this day, the Astronomer Royal is obliged to open the door at any hour of the day or night to anyone who shows up at his residence. So it's part of the job. You know? And they can blame Edmund Halley for that.
With the gun or not?
Oh, I don't know about that. But so someday when you're in London, you want to have fun, find out where the astronomer lives, show up in the middle of the night.
So when we do the museum trip, we'll be doing this.
That's right, that's right.
All drunk as hell.
Yeah, that's right.
They should be up anyway tonight.
It's night. He's supposed to be looking through the telescope, isn't he? So in any case, so he showed up, and he had this invention in mind, which is a big thing. I mean, it's a big object. Now the case that it was in, because it had a case, no longer survives, but the clock itself does, and it pretty much runs. But there's a bunch of interesting features to it, to the case clock. It's not a pendulum clock, but it has these 2 counterbalances with these steel weights at either end, and you wind it with a spring. And Harrison invented a device that would allow the energy built up in the spring to be released at regular intervals. And that energized the rotation of these 2 arms that went back and forth away and towards each other by this spring. So the energy was used counter to the spring. So if you notice where these 2 almost join together, okay, there is a wire band that goes around one and goes over to the other. There's kind of a little X there. And if you note that little curve that they go around, that curve is Christian Huygens' cycloid. Okay, it's that cycloid that regulates the movement of these pendulums in a perfect regular motion, similar to what the cycloidal cheeks on a pendulum do. So he was able to translate a pendular motion into this oscillating motion that he made his clock work. And he was able to get it to work through heat and cold and so forth. Now he would come up with different clocks to solve some of the problems. Ultimately 2 and 3 were bigger and slightly more elaborate, not necessarily bigger, but more elaborate versions of his H1 device. One of the things he did though was when he had 2 of them, he would put one inside next to the fire after having rated both of them against each other, and then another one outside, and then he would switch them. And it was the first instance of something resembling a double-blind experiment. So he also invented that. At least he's attributed with the invention of the double-blind experiment. Well, he was a eccentric character, and this was Charles Wager, who was instrumental in sending Anson's fleet around the world. Said of him, the man is said by those who know him to be a very ingenious and sober man, incapable of finding something more than he has already. If he can find encouragement, I desire therefore that you will see the man be used civilly, and that you'll be as kind to him as you can. That was after he interrupted Halley, and then this was a letter written by Wager to Democrat Captain Proctor, who was the guy that took the H1 and Harrison's son to Lisbon in HMS Centurion when she was a brand new ship in 1736, prior to Anson taking her around the world. So this whole thing began to attract people's interest and also their derision as this cockamamie scheme and a useless expenditure of public funds. Samuel Johnson wrote that this would supply the world with another instance of fruitless ingenuity. Harrison made no count of me in my shabby coat, for he had lords and dukes with him, because Harrison now suddenly was rocketed into rock star fame, and that was by the painter John Gainsborough. And then Benjamin Franklin, who visited London I believe in the 1740s, wanted to see Harrison's shop, and a fee of 10 shillings and 6 pence was charged to see his longitude clock. Now, if you read Donald Sobel's book, it appears as though from the book that Harrison should have gotten the award to begin with, and he just kept getting strung along by the perfidious, intransigence of Maskelyne and this whole bureaucratic apparatus that didn't want to recognize his genius and pay him the money. In fact, Harrison was raking in money hand over fist because his shop was by far the largest tourist attraction in all of London. Everybody was coming by and paying him to see his workshop and his clocks. He was one of the most famous people in London, hence Benjamin Franklin's visit. He kept working.
Everybody thought he was actually making the clock.
Well, he was making the clock. He had lots of people working for him at this point, but everybody wanted to see these things because he was like the original mad scientist, And it was fascinating to people, and watching these clocks with their interesting motion. Nobody had ever seen anything like it. It was really popular, and Harrison charged people to go. And so, in actual fact, Harrison just was dragging his feet and going really slowly. And at the same time, he was getting an ongoing flow of grants coming in from the Royal Observatory, as well as charging a lot of money for people to visit his lab. So he had turned science into a tourist attraction, and also, he's also rightfully credited with one of the first for-profit scientific labs in the world, right? Because he kept getting grants. So he's working on soft money, both in people visiting his lab and also by the ongoing thing. So his story ends up sounding like kind of a morality play where somebody is falsely denied the recognition and the money they deserve after he won the prize fairly, when he never was eligible to win the prize to begin with. And second of all, he ultimately made it's been calculated, almost 40,000 pounds during this period by charging people to visit his shop and by the ongoing grants he got from the government to continue his research into a horological solution to the problem. David?
10 shillings and 6 pence to visit his shop is a thumping big fee. That's a lot of money.
Yeah, it was then, definitely. Yeah, I mean, and people really wanted to see this. And when this whole thing about Harrison made no account of me and my shabby clothes, for he had lords and dukes with him, he also had patrons among the well-to-do who would actually pay him for having his workmen make clocks as well. So he was also pumping out clocks also. So he was actually working this pretty well. So instead of being this guy who was sort of myopically focused in his genius on just the solution to the problem, he was a pretty sharp operator. He made really powerful political connections among the political elites of London, and at every turn he outflanked his adversaries like Neville Maskelyne, because they were just not as politically connected as he was, and actually he was a smarter politician than they were, which is not the guy you read about in Doffel's book at all. He's actually a much more interesting guy, I think, and he was actually capable and contributed in a much more interesting way to the development of science and the method that science has for solving problems. I don't really, I mean, it's difficult to say, so let me think. About this period, 10 pounds was a pretty good salary for the master mariner of a sizable vessel, 10 pounds annually. So he's charging a lot of money. So these are pretty wealthy people. So it was actually Robert Hooke who invented the bimetallic strip, but Harrison claimed that he had invented it. And he put it to work in his devices because it was an attempt also to deal with differences in temperature. He invented something called the spring remontoire, which was part of his escapement that allowed energy to be released. And again, these machines continued to be more elaborate, building up to H3 in 1757. So these were not little things. And if you do go into the Greenwich Observatory, they've got them all lined up and they're all still working. All except the last one, all except H4, which has not been working for years. So suddenly, though, everything took a sudden turn from building these large, really impressive machines, which actually I think Harrison was intending to capture popular imagination because they were big and impressive and the things wave back and forth. And you look at them and they meet everybody's expectations for what an incredible time machine would look like. And instead, he was presented a watch by one of the guys that was working for him named Thomas Jeffries. Now that watch has since been destroyed. It happened to be in a building that got bombed in the Blitz, and so I don't think it even exists anymore. But Harrison got this watch and he'd never seen anything like it. And he decided, okay, this is pretty amazing. It didn't have any of the balance beams going back and forth and the other things, but it was incredibly sophisticated mechanically and from an engineering standpoint. And it kept really almost perfect time. So Harrison disassembled it and used it as the basis for his fourth clock, the famous H4, which is what he finally submitted for the prize. Now what's interesting is, this is Harrison's most famous portrait, showing him at the moment of his highest glory, holding a clock. That clock is actually the Jeffries watch, it's not H4. So, interesting. In any case, it's reckoned that it took like 20 or 30 different occupations to produce a clock like this. You know, the people that painted the numbers on the dial, the various little elements, tiny elements that had to be made, they were separate occupations. This instead is H4, which he developed in 1759. And as he said, I think I may make so bold to say that there's neither any other mechanical nor mathematical thing in the world that's more beautiful or curious in texture than this, my watch, our timekeeper for the longitude. So this was his final, well, it wasn't actually his final clock, but it was the one that he thought would finally solve the issue. Mind you, he knew he was never going to get 20,000 win the longitude prize, and indeed he never did. But he did expect to get a final payment of 20,000 pounds from this. So in 1761, it goes to Jamaica in HMS Deptford and comes home in HMS Merlin with an error of 5.1 seconds, which gave an error of 1.25 nautical miles. That error of 5.1 seconds was incredible because none of the tests conducted in Harrison's lab or subsequently in the Royal Observatory did it ever make that kind of accuracy. Ironically, there was all this effort put into making sure these things would not be thrown off their rate by moving the ship. H4 seems only to work if it's being jostled around on a ship, which is, it's fascinating. They say a watch can be but a watch, and that the performance of mind, though nearly truth itself, must be altogether a deception. No one wanted to believe that it could be that accurate, but part of the reason no one ever wanted to believe it is because it just was not that accurate when it's sitting there in a stable environment, right? And that's always been mysterious, and it never has been that accurate, actually, just sitting there. So in 1764, it went to Barbados, in another Royal Naval vessel, HMS Tartar, and returned in the merchantman Elizabeth. The error was 1/10 of a second a day, which was unbelievable, and it gave an error over the entire voyage of 9.8 miles. So people just didn't want to believe it. Nobody had ever built a machine that was that accurate or that close before, including Neville Maskelyne. I said, okay, if you really want the 20,000 pounds, I need to see all your clocks. So some workmen from the Royal Observatory were sent to Harrison's lab, and they dropped a couple of them, moving them out, jostled them over carts, you know, as they went over the cobble streets of London, set them up in the Royal Observatory, and of course they didn't keep time because they'd just been like wrecked by his workmen. And of course H4 didn't keep decent time because it never did, even in Harrison's lab, keep that good a time. It had to go on a ship, evidently, to do that. So H4 did not go with Captain Cook. And indeed, no chronometer went with Captain Cook on his first voyage in HMS Endeavour. Captain Cook instead took with him Neville Maskelyne's tables for lunar distance, which he employed successfully in finding Tahiti, which actually his immediate predecessor in HMS Dolphin, Captain Samuel Wallis, had determined the longitude of Tahiti by Maskelyne's tables, and that was part of Cook's sailing orders to go there to observe the transit of Venus. So he used those, and it worked fine until the Nautical Almanac they only published it for a certain period of time, so he ran out of time and then had nothing to get longitude from for the remainder of his voyage home from about the far far western Pacific home across the Indian Ocean. So for his second voyage, they wanted him to test chronometers. So of course he was going to use a table of lunar distance. He also had dipping magnetic needles, which he couldn't stand. He didn't think they were worth anything to determine longitude by magnetism. And he had 4 chronometers with him. Now 3 of those chronometers were made by a guy named Thomas Arnold, who was one of the foremost horologists of the day. And they were all exact duplicates of H4. Harrison had to surrender H4. They took it apart and they made exact duplicates, or Arnold did. They were all exquisite machines, and Cook had 3 of them. And then, just at kind of a last minute thought, another horologist, who wasn't really at that time as well known or as highly regarded, named Larkham Kendall, was paid £500 for his chronometer, K1. And so off Cook went on his second voyage on Resolution. So the 3 duplicates of Harrison's chronometer never worked decently. They were just all over the place. But Kendall's chronometer, made to a different principle entirely, was as fantastically accurate as Harrison's H4 was, to the extent that Cook literally couldn't believe it. And he was, at one point he was sailing in company with another ship, almost home, sailing for Madeira, and there was another ship in company, and they sailed up close enough to go through speaking trumpets, and the captain of the ship said, what position do you make it to be? And he gave the latitude and longitude. And he says, sorry, what longitude did you say that was? And Cook gave a longitude. He goes, I think you're several hundred leagues off. And Cook says, well, you just wait 6 hours, you know. And 6 hours later, the island came up, you know. So Cook was not known for a sense of humor, but occasionally, you know, he was able to exercise it. So this was a fantastic machine. Harrison did make an H5, and Kendall made another famous chronometer called K2. K2 went with Captain Bligh on HMS Bounty, and when his crew put him in the longboat, they didn't give him K2. So they used K2 to fix the position of Pitcairn Island. It was there for several years and was brought back home by the guy who discovered the Bounty mutineers on Pitcairn Island, Thomas Folger, and it made its way back to England and lived an adventurous life, and you could see that in the Greenwich Observatory also. There's also this reference, and this is the result of many novels and mysteries and stuff, Harrison's mysterious K6, which no one has ever seen, but Harrison referred to, and he was, at this point in his life, he was very secretive, and it was like Thomas, like Hook, you know. He didn't want to write about me. He said, there's nothing like this on Earth, nor ever will be again. And so that kind of got mystified and elaborated into maybe Harrison was working on an actual time machine that you can go back and forth in time, and kind of references that got picked up by H.G. Wells and so forth. So Harrison ended up, like a lot of these stories, stimulating, you know, novels and fiction and that sort of thing as well. So it was a, you know, again an interesting set of stories that evolved from this. Harrison was at one point approached during his development, his research, when England and France were at war, and the French offered him quite a bit of money if he would make them a copy of H4, which he refused to do. He said mainly they just didn't offer me enough money. That was his public complaint. You know, the French are just too, you know, cheap shit to pay much attention to. He wanted more money than that. So in any case, this began a proliferation of people making chronometers, but really it wasn't until the 19th century that they were inexpensive enough and widespread, their use widespread enough to actually make a difference in how people were navigating. Right up through, all the way through the 19th century, there were more people typically that were trying to find longitude using the lunar distance method than were using chronometers. So there you go. And I'm kind of talked out for the evening. Are there any questions about any of that? All right. Oh, one question. Yes.
Sorry. You mentioned that H4 doesn't work anymore.
They decided that if it's an important historical object, and that to keep a clock working that way, parts wear out and you have to replace them. So if they just kept doing that, pretty soon you wouldn't have H4 anymore. It would all be composed of all new parts. So rather than have that happen, what you're seeing is the actual H4. One other minor little story. There was a guy in the 1930s who is a Royal Navy officer named Rupert Gould, and he had had a nervous breakdown due to PTSD that he had acquired during some pretty traumatic experiences in World War I think including the Battle of Jutland. And he was still a commissioned officer, and rather than like kicking him out of the Navy, they said, hey, look, why don't here's something you can do for us. Back down in this old dusty room in the Royal Observatory, there's these clocks. Do you think you could restore those? And he goes, well, I don't know. I've never done that before. Okay, I'll give that a go. And that was his job in the Royal Navy, was restoring the clocks. That turned out to be H1 to H4. So he restored them all to perfect working order and wrote a book about it called The Marine Chronometer. And he actually managed to, it was therapeutic for him to restore these things and write a book about it. And then he started a radio show called The Most Intelligent Man in the World, and he would expound on things, and people would call in with all kinds of questions for him, and he would answer them. And it was one of those early talk shows on BBC, and it was Rupert Gould, it was Commander Rupert Gould, the most intelligent man in the world. But he got to be that because he was the inheritor of, in a way, of Harrison's genius and the restoration of those clocks. And the clocks you see today, in perfect condition in the Royal Observatory, are the machines that Rupert Gould had restored from basically unworkable condition after they'd sat for years and years in the back room.
There was a guy in, I think, in the Longitude movie that was repairing the clock. Is that the guy?
Yeah, that's probably Rupert Gould. Yeah.
Okay.
Yeah. Interesting guy. So there you go. And his book still is the definitive book on the history of the chronometer, even though he wrote it in the 1930s. Okay, everybody. Thank you. Have a good evening.